Okay, so good afternoon. Today, the first topic that we're going to talk about is about the relationship between wood and water. So, basically, we will see that unlike the other structural materials that we know well, like concrete or steel, wood is basically affected by moisture. Let's say it's affected by relative humidity of the environment. So in general, wood is defined also as a hygroscopic material, so materiale hygroscopico, because it's basically exchange water, moisture content with the environment. So you can see that this quantity that we're going to define today, which is called moisture content, is very important because it affects the strength of wood. So the strength of wood is also dependent on the moisture content of the wood. In general, the greater the moisture content and the lower the strength. First of all, definition. What do we define as a moisture content of wood? You see here, moisture content is defined as the ratio between the weight of water that we have into a timber wood specimen and the weight of the dried specimen. Of course, usually we express this as a percentage, so we multiply by 100. So the moisture content, it depends on several variables. So first of all, it depends on the environmental relative humidity. You know that when we are talking about an environment, there is two properties that in some way measure the climate. Climatic conditions are relative humidity and temperature. So the moisture content of timber is mostly affected by relative humidity, but also by temperature. But as I said before, more by the relative humidity. Obviously, as you know, the relative humidity in some way measures the vapor, the quantity of vapor that is present into the air. So clearly, the moisture content of wood, which is basically water, will mostly be affected by the relative humidity, so that by the quantity of vapor that we have in the air. As you know, 0% means 0% of relative humidity means no water into the air. 100% means that we are at the saturation point. So basically, 100% we are in a fog or in a cloud. So we see white around, because then we have a condensation of water. So between 0% and 100%. The relative humidity of the air. Now we are talking about moisture content of wood, which is something different. We said the moisture content depends on the environmental relative humidity, first, the temperature. Second, on the seasoning of wood. What does seasoning of wood mean? In Italian we would say stagionatura del legno. So seasoning means that we cut our wood, and once we cut our wood, we make it to season. So we expose to the environment, and we wait some time in order to allow the wood to dry. Basically because, as I said before, we can't use wood with very high moisture content because the strength would be very low, and there would be a number of other problems like distortions of the material that we are going to discuss shortly. So seasoning of wood, basically if we have just cut our piece of wood, the moisture content would be very high. If we have a piece of wood that has been cut and left into the environment for a long time, then the moisture content would be in general lower. Third thing, depends on the cross-section of the wood metal. If we have a very small piece of wood, in general the moisture content will change instantly because this cross-section is very low. Instead, if we have a very big cross-section, it will take I would say months before the moisture content of the cross-section is reduced to an acceptable level. Is it okay what we discussed so far? Clear, more or less? Clear also for you? Okay, good. Sometimes if something is not clear, you raise your hand and we want to translate in Italian. Try to do a short explanation in Italian. In general, we already discussed yesterday also before, the higher the moisture content, the lower the strength. Strength and stiffness, both of them are negatively affected by the moisture content. And also you see the greater the creep coefficient. So shortly, probably already today, we are going to talk about creep. You probably already know something about creep, probably you should have learned something in the course Laboratorio Costruzioni CICP with Professor Gagliotta. For the other, for the Turkish guys, probably you already learned about creep or creep coefficient, talking about reinforced concrete design, I think. No, never? Anyway, we're going to talk later because for timber it's a very important phenomenon. So I'm going to start from scratch basically to talk about creep. So the creep coefficient, the creep is in general it's a negative phenomenon, so the higher the creep coefficient, we will see the higher the reflection of the beam. And as you can see, the higher the moisture content, the higher the creep coefficient, so the higher the reflection. So this is another good reason why we have to keep the moisture content not too high in order to reduce the deflection of the beam and so the creep coefficient. First of all, how do we measure moisture content? We have two methods. The first one, if you want the safest one, is basically to overdry the timber specimen. So you cut a piece of wood. You weight it, this will be the wood with water. You weigh the wood with water, you take note of the weight, and then you put it into an oven, you dry it, you keep it at 112 Celsius centigrade for a little bit of time until you have completely dried, and then you weight again the wood. So the difference between the first weight, wood plus water, and the second weight on the wood is basically the weight of the water. So we divide the weight of the water by the weight of the wood after drying and multiply by 1. In this way we get the moisture content of wood. Obviously this is a very precise method, but we have two problems here. First of all, we will get an average of moisture content over the cross-section, not the local distribution, because in general the distribution is different from outer fiber and inner fiber. The second most important problem is that in order to measure the moisture content of a timber beam in this way, we need to cut a piece, which is not very nice. If later we're going to use this beam, on the building side. The idea is that once you get your beam delivered on the building side, you shouldn't cut any piece, because then you should classify the beam again. So this method cannot be used to measure the moisture content on the building side. Sì, allora in Italia. Have you understood in English what I said so far, or do I need to repeat? No, okay, I have to repeat in English and Italian. Okay, so the point is this, that if you want to measure the moisture content of a beam, suppose you are in a building site, you receive a beam, which is delivered by later, but you need to measure the moisture content, because you need to know that the moisture content is within a certain value. To use this method, you need to cut a piece of wood from your beam and then to do this kind of procedure. But when you receive a beam on the building site, you can't cut a piece of wood, because the beam has already been classified. As soon as you modify, you cut a hole, you cut a piece. This beam is no longer classified for the strength class that you have used before. So you can't use this one. Chiaro adesso? No, ripetiamo in italiano. Appena ricevete questa trave in cantiere e dovete misurare il contenuto di umidità, per misurare il contenuto di umidità dovete tagliare un pezzo, una fetta. Però voi non potete, siccome quella trave è già stata classificata, non potete manometterla, non potete tagliare pezzi, un pezzo di qua, un pezzo di là, no? Quindi non potete misurare il contenuto di umidità in questo modo. Chiaro? So we need another way to measure the moisture content of wood. What is the other way? Is to use these electric moisture meters. Basically, it's an instrumentation like this. This instrument has two probes, so basically you embed these two probes, needles into the wood, then you switch on, and you get a kind of electric circuit between the device and the wood. And basically the moisture content depends on the electric resistance between these two probes. So in the end, this instrument is going to measure the electric resistance between the two probes. From the electric resistance, we can then determine, we can then calculate the value of the moisture content. Of course, the problem of this instrument is less precise than the other one and needs to be calibrated on the wood species that you are using. So the same instrument used for two different wood species does not necessarily lead to the right value of moisture content, because the moisture content depends on the strength of the electric resistance, and the electric resistivity could be different from spruce, for beech, for other wood species. Okay? Okay? Good. So this is the instrument. So basically, on the building side, when you have to measure the moisture content, you use this instrument. If you got that, even if you have to buy, for example, some parquet for your house, it's always a good idea to measure with this instrument the moisture content of your wood. Because, as I said before, it's very important that the wood has been seasoned. So the moisture content is low once you get your wood delivered. Because otherwise, if the moisture content is high, you can have a number of problems, potential problems. Now, let's have a look to this slide here. Here you can see we have a living tree. You learned last week that the microstructure of a living tree is basically done by a number of straws, those cells. Those cells have a cavity inside, which is called cell lumen. So when the tree is alive, the idea is that the tree is full of water. The water will basically go up the tree and saturating all these holes, all this lumen of the cell. So when the tree is alive, it's full of water. All these lumens, cell lumens, are basically full of water. If you want to measure the moisture content of the living tree, you will end up with a value between 40 and 200%. So 200% of moisture content means that you have 2 parts of water and 1 part of wood, if you want, in the end. So it's more water than wood, more water than soil. So a living tree is full of water. When the tree is cut down, what is going to happen is that the amount of water starts decreasing. The water present in the woods can be defined as a free water, the water which is contained in the cell lumens, so those cavities, and bound water, the water which is present in the walls of the cells. So also the walls of the cells have some water inside. In this case, it's called bound water because the molecules of water are basically bound with the molecule of the wood. There are some kind of interaction, hydrogen bonds and van der Waals forces. Some of you might recall in chemistry talking about van der Waals forces. So there are kind of interactions between the molecules of water and the molecules of the wood. So free and bound. Why do we make this distinction? Again, we said the free water is the water filling these holes inside this lumen, and the bound water is the water basically filling or present in the walls of the cell. Okay, it's clear? So why do we make this distinction? Okay, let's have a look here to this schematization of a cell. A typical cell of the wood it's like a straw we learned last week. So it's a long-shaped cell. And it has a lumen inside, the cell lumen, which is basically this cavity. Now, when the tree is alive, we said that all these cell lumens are filled with free water. So the water in the cell lumen is called free water. And all the cells are full of water. There are also some water molecules tied or linked, bound to the wall of the cells with these van der Waals forces. So free water, bound water. The bound water is within this region here. As we said before, when the tree is alive, the moisture content is very high, 200%.
Sorry.
Sì.
Bound water means?
Bound, literally bound, in italiano sarebbe acqua legata, però non è che si traduca così. perché non sapreste mettere tutto, si tratta di acqua che in qualche modo è vincolata, come detto?
Cristallizzato.
No, non è neanche cristallizzato, perché poi deve... Com'è? Sì, è una sorta di combinazione, una sorta di interazione chimica. Cioè, è presente come molecole legate con queste forze di Van der Waals. Ok? Non è libera, qui l'acqua può scorrere, lì dentro invece è legata proprio. Una sorta di interazione chimica. Quindi per questo si chiama acqua legata, cioè legata, non si traduce acqua legata. Ok? So 200% living tree, we have all the cell movements are filled with water, and also there is lots of bound water also within this cell walls. Then we said once we cut the tree starts losing water. The water starts basically moving outside. So first, the tree is going to lose the free water. You see here, we have a part of free water is no longer there. Then, as the time goes by, we will arrive to a condition which is called fiber saturation point, punto di saturazione della fibra. The fiber saturation point is the value of the moisture content, where all free water has gone, and there are still bound water filling all the gaps within the cell walls. Okay? So at the fiber saturation point, which is usually 28%, 29%, the timber has lost all the free water, but no bound water. If we keep leaving the tree outside, what is going to happen then? We're going to get also less bound water. So also the bound water is going to be reduced. As you can see here, above the fiber saturation point, basically, since we have just lost the free water, there is no significant change in size of the cell movement, of the cell themselves actually. So the cells are always the same length and the same width. Once we go below the fiber saturation point, since we are going to lose water which is bound to the wood with these van der Waals forces, the wood starts moving. You can see here that we have a shrinkage. So the cell is going to be a little bit shorter, and particularly is going to be narrower. So the cell is going to reduce the diameter more than the length. So the length is more or less the same, it's reduced just a little bit, but the diameter is going to reduce quite a lot. If the water keep on going away, you can see more and more the cell becomes slender and slender, more and more. So, we said before, the fiber saturation point is this point here. And you can see that there is a significant difference between having a moisture content above 28%, so above the fiber saturation point, or below the fiber saturation point. Above the fiber saturation point, basically, any moisture variations, for example, due to the environment, will not affect the size of the wood. While instead, below the fiber saturation point, if you have a wood, if you have a moisture content variation, particularly if you have a moisture content decrease, then you will get some shrinkage. So shrinkage in Italian is called ritiro. Of course, if you go down and then you go up again, then you get swelling, rigonfiamento.
Why did we choose the middle one? Because of the shrinkage starts after.
Because the shrinkage starts only from here to down here. Here there is, as you can see here in the figure, there is no shape variation and no size variation of the cell. So no shrinkage, no variational, no dimensional variations above the fiber saturation point for any moisture content variation. Instead, below the fiber saturation point, you see there is shrinkage. Shrinkage if you go down with the moisture content, or swelling if you go up. So this is a very important definition of the fiber saturation point. Another important thing is we need to keep in our mind the shrinkage, because wood is an anisotropic material, the shrinkage is mostly across the fiber. So longitudinally, parallel to the grain, there is hardly any shrinkage. So you can see here, the length is more or less the same. Instead, the diameter is much smaller here. Okay? So we will see that the shrinkage parallel to the grain is almost negligible. Instead, the shrinkage perpendicular to the grain will be quite important. Okay? Good. Another important remark. The mechanical properties of wood, so we said grit coefficient, the modular elasticity, strength, are not affected by moisture content above the fiber saturation point. So here to have 15%, 100%, the strength doesn't change. Instead, below the fiber saturation point, the lower the moisture content, the better the mechanical properties. Okay? So basically, this is just a summary of what we have just said now. Now, we can ask ourselves, why does the moisture content of timber keep on changing in time? As I said at the very beginning, because wood is a hygroscopic material. So it continuously exchanges moisture content with the surrounding environment. So if you take a small piece of wood and you put into a certain environment characterized by relative humidity and temperature, immediately the moisture content of wood will change and will move towards what is called equilibrium moisture content. So the equilibrium moisture content is the value of the moisture content of wood that is associated to a certain environmental conditions. So a certain relative humidity, a certain temperature. So the value of equilibrium moisture content exists for any value of temperature and relative humidity environment. There are some diagrams like this that you can see shows the variation, the dependency of the equilibrium moisture content of wood upon the relative humidity and upon the temperature. So the idea is that the equilibrium moisture content is the value of the moisture content that is going to occur in a very small piece of wood surrounded by an environment characterized by a certain relative humidity and a certain temperature. Okay? Which value of equilibrium moisture content can you get, for example, in an environment characterized by 60% relative humidity and 21 Celsius degree temperature? You use this plot here, you start from 60 until you reach the curve at 29 degrees, and then you can end up with equilibrium moisture content, which would be like 11%. This means that if I put a very small piece of wood into an environment characterized by 60% relative humidity and 21 Celsius degree temperature, we will measure immediately, I would say after a few seconds, we will measure this small specimen, a value of equilibrium, or a value of the moisture content equal to 11%. So this is defined as equilibrium moisture content. There are also some other plots. For example, in this case, you can see here the curves are for any value of moisture content. Here we have relative humidity, here we have temperature. So at the end, again, same example as before, 20 degrees, 60%, then we need to interpolate here to find out the curve. So if this curve is 13% moisture content, this is 12, more or less, we get 12%, 12.5%. As you can see, there is a more difference between this plot and the other. Then one we get 11%, 12.5%. Those curves, strictly speaking, are different from wood species to another wood species. So they're not exactly the same. So perhaps this curve was, this plot was done for New Zealand radiata pine, the other one was done for European spruce, and that's the reason why there are those small differences. So, the equilibrium moisture content depends mainly on the relative humidity of the environment, we already said before, but also the temperature of the environment, and slightly also on the type of wood. So it's not the same, of course, any spruce or hardwood or something different. Another important thing, these values of equilibrium moisture content can be reached quickly only in small specimens. So only if you have a very small specimen that you put into a certain environment, then you can reach the equilibrium moisture content. Because if you have instead a bigger, large size structural wood, timber, for example, a big cross section of timber, then you put in the same environment and then you want to measure, you will find that target moisture content, equilibrium moisture content 11%, only in the exterior fiber, not in the interior fiber. Why not? Because there is a resistance of the wood against the moisture propagation across the cross-section. So, you will find on the outer fiber the equilibrium moisture content, then as you go inside, you will tend to find higher value of moisture content. So remember that the equilibrium moisture content is true, it is reached quickly only in small specimen. If you have a big specimen, you have to allow for more time in order for, in this case, for example, the moisture content that you have in exceedance inside here to basically move outside the cross-section. And in this case, we have some equation, differential equation, called Fick's law. Perhaps you studied the Fick's law for some kind of diffusion phenomenon in physics or some other disciplines. And basically, depending on the composition of wood, you may have that the moisture content will flow outside faster or slower.
Why are we talking about equilibrium?
Because this is eventually, in the end, this is the value of moisture content, where also this cross-section will tend to, but in the long term, not immediately. Because we are interested, in the end, we are interested if, for example, we have to build a swimming pool. We have to know that in a swimming pool, in general, you have relative humidity quite high. So we are interested in the moisture content that we can expect for this certain kind of environmental condition. Why we are interested in the final value of the moisture content? Because, as I said before, from the fiber saturation point to the moisture content, we have a variation in the size. So we have what we call shrinkage. And unfortunately, the shrinkage not only this makes a distortion of the cross-section, but also may lead to some failure, some cracks. So very often when we see cracks into the wood, they are not due to structural failures, but they are due to the ideal stresses, so that let's say the autotensione in Italian, that can arise in a cross-section due to the moisture content variation, due to basically this kind of movement, this volume variation that takes place in the wood. So we are interested in equilibrium moisture content because, again, depending on the final destination of our building, we need to understand which would be the final equilibrium moisture content that we can expect in our room. So, to design a structure for a sauna is not the same that to design a structure, for example, for a dry environment. So the final equilibrium moisture content is different. Equilibrium moisture content, in the end, given us, also in this case here, it will be a matter of time, but in the end, if we keep the environmental condition constant over time, in the end will take perhaps months, but in the end, all the fiber will tend to go to this values with 11%. Okay? Very important thing. If you just remember how is the microstructure of wood, you will understand that obviously the resistance of the wood to the moisture flow is much higher along these lateral surfaces than on the ends of the cross-section. Why? Because of course our cell lumens, our fiber are oriented this way. So it's much easier for the water to go inside the wood from in this direction, because they will find directly the straws there, like the channel, free channel, rather than in this other direction. So remember that if you are concerned about, for example, if you're using wood outside, if you're using wood outside, chances are that the relative humidity will be high, maybe there will be also rain, like today. And then in this case, of course, if you leave this one without any sealing, you will have lots of flow of water and moisture content through this surface here. So it's a good rule is to protect, to seal the surface in order to prevent the penetration of water through this surface, because there we have all the lumens of the cells. So we said before, Do you stand out?
Because parallel to grain, cioè nel senso la domanda
No.
dovrebbe essere la dizione perpendicolare alla filatura.
Allora, piece of wood exchanges moisture content mostly through the end section. This is one end section, and this is the other one. Parallel to the grain. So maybe it's not the word. The idea is that a piece of wood exchanges moisture content parallel to the grain. Mostly parallel to the grain. So the exchange is much higher.
Not the section, so parallel to the grain.
No. Okay, so we can write in better English perhaps. Mostly parallel to the grain through, we'll say this way. A piece of wood exchanges moisture content mostly parallel to the grain now I want to say that the piece of wood exchanges moisture content mostly through the end section. So this is important. If I write it here in the direction, we make it clear. It's better as well. Okay, so when the tree is cut down, the moisture content will reduce from 100% to the equilibrium moisture content for the given temperature and relative humidity. In general, the equilibrium moisture content for the normal range of temperature relative humidity that we can expect is between 8% and 30%.
Sorry, can you come back to the other slide? How do you know which is the direction parameter?
Because, let's have a look. It's quite obvious once you look at wood. So in the end section you see also the raw tree. This way, or maybe this way. In the other way, you see it this way.
So this is the direction parameter.
Yes, this will be the trunk, so this is parallel to the grain. So here, you can also see by eye that there are some small columns, which are the lumens of the cells. And so the penetration of water in this direction is much easier than here. Okay? So we said before, when the tree is cut down, the moisture content starts decreasing from the value in the tree, 100%, till the equilibrium moisture content, which we said normally between 8% to 30%. For the normal value of relative humidity that we have here in the freezer. As we said before, the larger the cross section, the longer the drying process. So, the mechanical properties, we said before, they are worse for wet wood compared to dry wood. Sometimes wet wood, so wood with high value of moisture content, is defined as green. So green wood means wood with high value of moisture content, wood that was not dry, basically. So moisture content 25%, dry wood 16%. It's not very dry. This is taken from New Zealand standard. For us in Europe, a dry wood would be at the moisture content of 12%. So we regard the wood as dry at 12%, more than 16%. But the environmental conditions in New Zealand are slightly different compared to Europe. So, green wood, you can see here, for example, bending strength for a green wood, what is green? Species. Dry. For dry, 10 megapascal, for green, 7.5. Quite a lot, but take 25% less. If you reduce the strength from 25, if you reduce the moisture content from 25% to 60%, you lose almost 1/4 of that strength. So this dependence is quite important. You see here, when we design a structure, we need to define what is the value, the final value of the equilibrium moisture content in this kind of conditions. This table helps the designer choose the right value of final target equilibrium moisture content. So you see, for example, structure inside the insulation between 14 and 18%, floor is not exposed to ground atmosphere 8 to 12%. You take an average value of this range. So the idea is that, for example, we are designing a certain type of structure for which we have a target value of our equilibrium moisture content of 12%. We know that the wood, once it is cut from the tree, it will be to 30% even more. So what we have to do, we have to dry the wood, the timber. So we have to reduce the moisture content as close as possible to the final target value of the equilibrium moisture content. How can we dry wood? We can use two methods, the so-called air drying or the so-called kiln drying. Kiln drying means, in Italian, essiccamento in forno. So air drying, this was the method that was used particularly in the past. The idea is that we need to cut the wood in smaller cross-section, if possible. Of course, this is not always possible because if you want to use a big strong timber, then you have to accept that this would be also the size of the wood. So it won't be so low. And then you see, you need to fillet the timber, stack, and allow to dry with the passage on natural air. You might have seen actually when you go in the countryside, perhaps not so much here, but more in the Alpine region. Sometimes we have this kind of piles of wood. Of course, what is missing here is a roof, as you can imagine. You can't have this one without a roof. Because if you leave it outside, it's a day like this, you have rain, and then you lose immediately. Your water can immediately, again, increase the moisture content. So you must have a roof above. Of course, this kind of air drying may take several weeks. It depends on the cross-section. If you have a small cross-section, it doesn't take very long. But if you have a big cross-section, it takes also months, even years. So, I would say that in these days, nowadays, almost everywhere, we use the kiln drying, which means that we have to put this same kind of configuration rather than left outside, is put inside in this oven where there are heat and airflow in a control cycle. In this case, maximum longing, usually 2 to 3 days, you can get at the end. Your wood may be dried to the target equilibrium of moisture content, 12%, 14%, what is required. So, why do we need to dry the wood? We already understood that the drier the wood, the better the mechanical properties. In the reality, I can tell you that this is not the main reason. For sure, this is a good reason, but this is not the main reason to spend money for this. There are other, probably better reasons to at least. One is that, particularly when we use glued products, we will see that, for example, when we construct a glue laminated timber beam, legno laminato incollato, we need to glue.
Sì, ti possiamo bloccare 3 minuti.
Ma loro si arrabbiano.
No, non si arrabbiano, sono tutti i colleghi che vogliono seguire per chi deve stare.
Ma just a moment, there's a good subsidy.
E io devo uscire, è responsabile.
Sono le ultime?
Sì, e le ultime. Abbiamo appena cominciato. Questo è
Cos'è il risultato del legge?
è di uno. E l'altro è questo che stava lavorando. Grazie ragazzi.
Okay, sorry for the interruption. So I was saying that the one reason, one very good reason is that when we need to glue the wood, so for example, glue laminated film, we need to glue the wood together, the glue may only go off, may only work basically, if the moisture content is below 40%. Otherwise, the gluing process doesn't work. This is one very good reason to dry the wood. And the other good reason is that if we don't dry the wood, we learned before that from the fiber saturation point till the equilibrium moisture content, so from 29% till 12%, we will have some shrinkage. So some basically dimensional variation. This dimensional variation, unfortunately, it does not take place without eigenstresses, which means autotension. So once the section is going to shrink, we will have also some eigenstresses, so stresses within the cross-section, and some of those stresses may become larger than the strength of wood. Particularly if we talk about tensile strength perpendicular to the grain. You remember that wood is very weak in tension perpendicular to the grain, so only small value of stresses perpendicular to the grain, for example, those due to the shrinkage, may lead to the structural failure, to the formation of a crack within the wood. So basically we want to dry in order to avoid the occurrence of cracking, the other problem, when the structure is basically constructed. We want to have this thing before the construction.
Ragazzi,
Sì.
posso dire italiano?
Allora, è italiano.
Nella prima parte, quando ha detto che se noi manteniamo alto il contenuto di...
Sì.
Ma non dovrebbe essere il contrario, cioè che ho un effetto tipo di scollante sul...
No, so the question is why we need to reduce the moisture content of wood in order to make the glue to go off. This is a kind of chemical thing. The glue is a chemical bond. I'm not an expert of gluing, but I imagine that if the moisture content is higher, then this glue, rather than adhere only on the wood itself, it has also to adhere on some molecules of water. This doesn't make it to work well.
Ah, ok. Quindi
Contrario, forse.
se aumento il contenuto non mi lavora per la...
No, esatto. So, the other important thing, why does this shrinkage create lots of problems like distortion and residual stresses? Because due to the anisotropy of wood microstructure, shrinkage takes place with different magnitudes along various directions. So basically, the shrinkage is not the same, we already saw, parallel to the grain and perpendicular to the grain. Parallel to the grain, there is hardly any shrinkage. Perpendicular to the grain, there is a significant shrinkage, but unfortunately, perpendicular to the grain, there is not the same shrinkage in the radial direction and the tangential direction. Remember that we have two different directions. The radial direction, which would be, let's say, this is the radial direction, and this is the tangential direction. So radial, the radius of the growth ring, a tangent direction, the tangent to the growth ring. So in this direction, the radial direction, the shrinkage is most half as much as in the tangential direction. So it's not that for strength. For strength, if you remember, we said, okay, the strength is the same in this direction, the other. Instead, for shrinkage, no, it's much higher in this direction than in the other. And this creates problem of distortion, like this section that you can see. This initially, as you can imagine, was a rectangular cross-section, and after dry, you see the shape.
How can I solve the problem that when the high tension are much higher than the strength of wood?
Then you get the crack. Yeah, the idea is that if you dry the wood before, then by a slow dry, we can avoid these cracks.
Avoid?
The cracks. We can avoid the fessura.
Ah, okay.
We can avoid this problem with the strength. Instead, if we, let's say, we put the wood before trying to put on the building side, in our structure, then we allow, this moisture content variation to occur later. So basically, we don't dry the wood. Then later on, we will have different conditions. Since also the wood is tied to the different parts, those restraints are additional and make it easier to get distortion and also some cracks formation areas. That's why we need to basically dry the wood before it is used to structural application. In fact, the idea is that after I dry a piece of wood like this, I can't use it this one. What I have to do, I have to plane it again. I have to plane it and to basically to lose a little bit of cross section to find again a regular rectangular cross section.
So if I dry the wood before, I don't have this problem.
If you dry before, you don't have this problem. Exactly.
Sorry, the shrinkage of the radius direction is...
Yes, now we're talking about this written here. Yes, in the radial direction, the shrinkage is half the shrinkage in the tangential direction. So we can define, you see, this quantity, shrinkage from green to 12%. So it would be the shrinkage is the length of the specimen at the fiber saturation point, minus the length of the specimen at 12% moisture content, divided by the length of the specimen at fiber saturation point, times 100. So, for example, this fiber saturation point usually 29%, 28%. So, if we move from 29% to 12%, we will have a shrinkage. So, we will have basically, you see, a shortening around all three directions. However, you see that in the longitudinal direction, parallel to the grain, we have a shrinkage of only 0.1%, so basically negligible. In this direction here, the shrinkage is negligible. Instead, in the radial direction, the shrinkage is 2.1%, and in the tangential direction, it's 3.9%. So you see this ratio, let's say 4 and 2, so twice. And in the other one, 0, basically. Okay? Another important thing is this plot here. This shows that the shrinkage, basically this is the shrinkage depending on the moisture content of it. So from 30%, we said that from 30% above we don't have any dimensional variation. From 30% to 0%, as you can see here, that as we decrease the moisture content, also the shrinkage increase linearly. This quantity here, SHR, was basically defined at 12%. So 12% you see 0.1%, 2.1 and 3.9%. So since there is this curve is a linear curve, what we can do, we can, if we need to calculate the shrinkage, so basically the dimensional variation along a certain direction, we can use a formula very similar to the one that we use to calculate the thermal expansion of a piece of material. So, example, this is our piece of wood. If you want to calculate here the shrinkage in one direction, let's call this one delta L shrinkage. So delta L can be expressed in this formula here, alpha U, which is called dilation coefficient of, actually no, in this case would be moisture variation coefficient, coefficiente di dilatazione legato alla variazione di umidità, times L times delta U. Sorry, delta MC. Variation moisture content. Exactly the same formula that we use to calculate the thermal expansion of material. So initial length times moisture content variation times times moisture content variation delta MC times dilation coefficient G due to motion moment variation. So this alpha u can be calculated as, for example, for the longitudinal direction, so alpha u parallel to the grain, we said that this is negligible. If you want to calculate, this will be 0.1 divided by 100 times 30 minus 12. So this is almost 20. In the end, you will get 0.00005. Something like this. But this is usually, as I said before, is negligible. We don't need to calculate. We can do this exactly the same thing for the other two values. The shrinkage parallel, sorry, in the radial direction and in the tangential direction. So you can see here that this difference between the shrinkage in the direction, in the radial direction, the direction tangential, leads to distortion of the cross section when we cut pieces of wood. You see here, for example, as I showed before, we don't have any distortion, any significant distortion, only for the pieces cut along the diameter of the trunk. In this case, you can see that a rectangular was before the shrinkage, the rectangle is also after the shrinkage. But in all the other cases, you see here, first is a rectangle, and then we have something which is called a bow. No, sorry, something which is called a cup, this kind of formation, or here, this square cross section after the drying process becomes a diamond. This circular cross section after drying becomes an ellipse. So the idea is that, as we said before, we cut the wood, then we need to dry the wood, and after it is dried, then we have to blend it in order to get the final cross section. The drying should be carried out to a value of moisture content as close as possible to the equilibrium moisture content of the environment in which this wood will be used. Okay? You see here, if we have like a log, for example, often we can use this kind of round cross section. If you have a log, of course, before without the bark, senza corteccia, this round cross section, if we allow it to dry naturally, also in the thin dry, at the end we will get, due to this anisotropic behavior, at the end we will have the formation of a crack. So often, in order to avoid this big crack, what they do, artificially they do a small cut with the saw. So basically, by doing a saw cut like this, this allows in some way these eigenstresses, these residual stresses to reduce, and so in the end we can prevent the formation of a big crack like this. You see here, particularly if the pith, so if there is a pith, so in Italian the midollo, you see here, if there is a pith. This is the pith from midollo. This is very weak because this one is basically, once you plant the tree, at the beginning the tree, of course, it doesn't have a strong trunk. It's like a small plant, so it's very soft. And after it starts growing, but at the beginning you see the pith is very weak. So this pith create some problems. You see, they induce this kind of cracks and so on. Here you can see typical drying cracks on a big cross section. So an important point, if you are using sawn timber, so solid timber, if you get big cross section solid timber, you have to accept that for sure you will get some cracks. So it's not possible to have a big cross section made of natural wood without any glue order, without any crack. Tell you this because often the clients, bioarchitects, so on, they don't want to use any glue, so they want to have only natural wood. Okay, that's okay, you can have it. Even though I would say it's a bit difficult nowadays for a big cross section, because you can get easily smaller cross section, but to have big cross section is not so simple. And of course, once you get the big cross section, you have to accept it. First, this big cross section will be delivered green with lots of moisture content, because no timber producer will accept to cut the cross section to leave it there for a couple of years, which is the time needed for this big cross section to dry. And second, so first you get a very wet wood. And then you have to accept that once you use this wood, it will dry in the next 6 months, 1 year, 2 years. And during the dry process, inevitably you will get cracks like this. And the crack can be also quite big. You can also go with your hands inside. So you have to be very clear with your client and say, okay, we can have a solid wood. Just remember, don't come and complain with me once you discover after a couple of years that you have this big cracks inside. Okay? Okay, how to calculate shrinkage or swelling of timber components? Very simple. We use this formula here. We already understood how to do it. Because the relationship is linear, so we can use this kind of relationship. So, this coefficient here, the moisture dilation coefficient of wood, is calculated, as you can see here, by calculating the ratio between the average shrinkage in the radial and the tangential direction, and the difference between the fiber saturation point and 12% divided by 100. Why do we use the average shrinkage, not the right value of shrinkage, in the radial direction or in the perpendicular direction, in the tangential direction? Because we cannot know a priori how our piece of wood will be, or our plant will be cut from the tree. So as you can see here, suppose that we are going to use a cross section like this. If this cross section here is cut here, then we should use the moisture dilation coefficient in the radial direction to calculate the shrinkage on the depth. Because of course after this is going to be used in the other direction, and the tangential one for the width. But if the same piece of wood was cut here, then it would be the other way around. This will be tangential, this will be radial. So it depends on when it is cut. Okay, it's clear? So this is radial, tangential. This will be tangential and radial. We cannot know, when we order a plank or a wood, we cannot order a plank cut in this way, or a plank cut in this way, or a plank cut this way. We don't know how these things cut. So since we don't know, the idea is that we just consider the average of the two values of moisture of the basically shrinkage in the radial direction and in the tangential direction. This way, our possible mistake will be minimized. Okay? So those are the values here. You can see more or less 0.0017. The value, let's call it perpendicular to the grain. The other one was 0.0005. So much lower. And this is the formula. So let's now make a small example. We have a lintel, architrave, made of wood, with this work brick construction. L is the length, D is the depth, and B is the width. So L 2000 millimeter, B 120 millimeter, D 300 millimeter. We want to calculate basically assuming that this lintel has been used green, so at the value of the moisture content above the fiber saturation point. We want now to understand what will be the shrinkage, so how basically the sizes are going to change after drying, natural drying, at the final moisture content of 12%. Now, suppose that the initial moisture content of this trichord is 50%. Okay? We don't know. We just know that it comes green. So, it could be 50%. How can we calculate, for example, the variation length from 50% to 12%? We use the formula that we saw before. This one. Alpha times L times delta. So alpha is basically in the direction parallel to the grade, in the direction of the length is 0.00005 times L. L is 2000 millimeter times delta U. How do you calculate delta U? In this case, we said 50%, and then the final value 12%. So delta U would be given by what? Sorry?
50 minus that.
Okay, here we need to be careful because 50% is above the fiber saturation point. So we said before that until the fiber saturation point, no variational changes will occur. So from 50 to 29%, there is no moisture variation. So it may be 50, maybe 1, but this doesn't matter. What really counts, to put in this formula here, is the variation between the fiber saturation point and the final target value moisture content. So we have to do 25 minus 12. So, you see here, 1.7 millimeter. So, longitudinal, due to this variation moisture content, quite significant, from the fiber saturation point to 12%, this linten is going to shrink by 2 millimeters in the direction of the length. So 2 millimeters out of 2000 is 0.1%. So basically nothing. Okay? Now, in the other two directions, we have a different value alpha U, because the direction is equal to the grade. We use instead L, the other dimension, and again, L times C will be always 30 minus 12, 29 minus 12. So, in the direction of the depth, 8.7 millimeter, in the direction of the width, 3.5 millimeter. So, let's say 8.7 millimeter, 1 centimeter. So, you can see here, this one, in the long term, is going to shrink by 1 centimeter. 1 centimeter out of 30 centimeter. What kind of problem may occur? The problem may occur is that all this part is going down by 1 centimeter. So once you walk above here, you will recognize that there is a small descent, 1 centimeter. So you can get a problem like this. So in order to get rid of this problem, what you have to do, you have to try to drive it. In the direction of the width, 3.5 millimeters, so instead that we set 120 millimeter, we will have 5 millimeter less in the direction of the width. But this is not important, it doesn't create any specific problem. So recall, it's very important. This shrinkage may become important in the direction perpendicular to the grain. Sorry, not in the direction, in the vertical direction. This is another example. So here we have, suppose you have here a reinforced concrete building, and you construct an extension to this reinforced concrete building made of wood. If you use, again, green wood, so wood that is not being dried, what you can expect is that in the long term, again, you will have a settlement here. So everything is going down a little bit. So how much down we can expect this new extension can go? We use again the same formula, where, however, we need to find out which member are going to contribute to the shrinkage. Just remind you, we said before that in the direction parallel to the grain, the shrinkage is negligible. In the direction perpendicular to the grain, the shrinkage is more important. So, if you want to calculate the total settlement, you can say that the total settlement here will be alpha u, which is the same, it's not this value, the other value that we calculated before, times delta MC, again will be 30 minus 12, or 29 minus 12, times the summation of all the members that are going to shrink. Which members are going to shrink in this arrangement here? Let's have a look. So this is called light frame construction. We are going to study this towards the end of the course. So this is called bearer. So this is, you can assume this one is kind of foundation. The bearer is what in Italian is called torniente. So it's basically a piece of wood that we have in this way. Let me just take this piece of wood so it's simple for me to explain what we are talking about. So this one is a piece of wood put in this way. Okay? Then this is a joist, piece of wood put in this way. Plate, piece of wood in this way. Then this is a piece of wood in this way. And then here another piece of wood in this way. Okay, it's clear? Now, in this formula, which value of L do I need to put to calculate the shrinkage? The biggest, this one. Are you sure? To think about it. I calculate the shrinkage of this member here, which is the longest. But which value of motion dilation coefficient do I need to use if the shrinkage is parallel to the grain? I have to use this value here, 0.00005, which counts hardly anything. So is it sure that this would be the most important contribution? We saw before that for a 2 meter length, this contribution is 1.7 millimeter. So this one is 2.4. So instead of 1.7, maybe it will be 2 millimeter. Is that the largest contribution? No. Which other contribution do I need to consider?
The direction.
Eh?
The direction.
Yes, but in the direction of which contribution? Of this one?
No.
This one I already considered. 2 millimeters. Then I have this member here. Do I need to consider the shrinkage here?
Yes.
Yes, in which direction?
The direction.
Yes, this one. Okay, so 50 millimeter. In this formula we have to put alpha, which is not this value but this value here, 0.0017. So 0.0017 times delta MC, we said is fixed, is 29 minus 12, times L. So L will be 50 millimeter. Finished? Or do we need to add something more? This one? 50, then something more, or it's finished? No, it's not finished. We have also one choice here this way. So, 300, then finished. And then the last one, also this, because in this way here. Okay? So at the end, I will have a formula like this. You see, 0.0017 times 29 minus 12 times, you see, 200. This, plus 300, plus 50, plus 50. I work out this number, 70 millimeters, so 2 centimeters. In the end, we can expect, if you don't write the book, we can expect that if we put this timber extension flushed with the reinforced concrete one, so the same level, later, after some months, I can expect it to have a step of a couple of centimeters. Okay? If I install the wood as a green wood. Instead, if I dry the wood, no problem at all. Okay?
In Italian, why we choose the master dilation coefficient equal to 0.0017?
Yes. In italiano. allora praticamente 3,9 sarebbe il ritiro dal 29% di umidità al 12%. Ritiro nella direzione tangenziale. 2,1 sarebbe ritiro nella direzione radiale. Siccome non sappiamo come verrà tagliato il nostro pezzo di legno, facciamo la media. 3,9 più 2,1 diviso 2. Siccome questi però riguardano il range da 29 a 12, e siccome qui invece nella formula questo coefficiente qua è per percentuale del nostro conto, no? Per percentuale di contenuto di unità, devo dividere per 29,12. E allora è per 100 per il percentuale. Allora questo qui poi lo posso moltiplicare per delta di 5.
No, però nelle prime esercizi che abbiamo visto, avevo visto che c'erano dei risultati trascurabili.
Sì.
Ad esempio il primo era trascurabile, il secondo no.
Esatto. Il primo, questa volta, l'abbiamo trascurato, non l'abbiamo neanche considerato. Il primo, se vi ricordate, il suo collega aveva detto, calcoliamoci il ritiro di questo. Se lo facciamo, otterremo, siccome l'elemento lì è lungo poco più di questo, otterremo 2 mm. 2 mm trascurabili rispetto ai 2 cm finali, no? Ok? Sì, grazie. Ok. Bene, un punto molto importante. Quando andremo a realizzare dei collegamenti tra gli elementi di legno, dobbiamo fare molta attenzione al fatto che when we are going to design the joints between the timber members, we have to be very careful about this problem with shrinkage and swelling. Why is that? See here, for example, this is a kind of pin connection between a timber column, timber post, and a timber beam. It has been constructed using a metal plate and some bolts. So this connection is a typical example of a pin connection, even though I would say more than a pin is a semi-rigid connection because it transmits also some bending moment. But irrespective of that, you can see that since we basically constrain these two fibers of wood to keep this distance fixed over time. Why is that? Because you see this plate is very stiff. The steel plate is much stiffer than the timber perpendicular to the ground. And the bolts are very stiff. So those bolts will basically keep this distance between the timber fiber constant over time. Now what is going to happen is this, for example, timber here is going to dry. So when we place the timber beam, it is at, let's say, 18% moisture content, and then the moisture content starts decreasing to 12%. What is going to happen then?
The fiber should compress and...
Exactly. So because of there should be some shrinkage. So we would expect a shrinkage in this direction here. Can the shrinkage occur freely without any stress? No. Why can it occur? Why can it occur? Look here, there are some bolts and some stiff steel plates. So the shrinkage cannot occur because it's blocked by the steel.
It is a isolazione.
No, forget about the cracking. At the beginning you don't have any crack. At the beginning you have a solid cross section, you know? Then this solid cross section would like to shrink, but it cannot because this steel plate and the bolts will keep the distance constant. So if it cannot shrink, what's going to happen? Some, we call in English idle stresses, so some residual stresses will occur perpendicular to the ground. So basically, this one wants to shrink, but it cannot because this distance is fixed. So if it cannot shrink, then it will get into tension perpendicular to the ground. So we will get some tensile stresses perpendicular to the ground. This tensile stress may be also very high, depending on the magnitude of the moisture content variation. And just remind you that the tensile strength parallel to the grain of wood is almost zero. It means that after a little bit of time, what is going to happen? The wood is going to fail, perpendicular to the grain. And then this crack is going to occur. As soon as the crack opens, then, of course, we have a shrinkage, free shrinkage of the two parts, and the stress goes to zero. But of course, then you have this crack, which is not very nice, doesn't have a very nice appearance on one hand, and on the other hand, also, the strength is a little bit smaller, of course, because you have a crack. You have only one cross section and two cross sections. Okay? So how to avoid this problem? To avoid this problem is basically to ensure that the wood is free to move inside the connection. How can we make the wood free to move inside the connection? We need to use ovalized holes or slotted holes in the steel. So basically, as you can see here, in the steel plate, we will have an ovalized hole. So we cut an elongated hole into the steel in such a way that when the wood is going to shrink, let's say this is the wood, for example, this is the hole, the balls going through will be able to go down. Okay? This is similar solution applied for a glue-lamp beam. Same concept. Okay, it's clear? Any question? We have to say that shrinkage is generally not a problem. It's glue laminated and LVL beams. So in engineering good products, when we use the glue, shrinkage is not a problem. Why is not a problem? Because as I said before, to be able to glue the pieces together, we need to dry the wood. So for the simple reason that the pieces are glued, it means they have already been dried. So shrinking in general is not a problem. However, problem can arise if the wood product is not protected from the rain after being manufactured. This is an example you see of a floor made from wood panels that were installed after installation. They got wet because of a leakage. Okay? So they got wet, so being wet, they start increasing the length. And then, you see, we get a situation like this. So remember, in general, when we deliver wood products should be always protected. Usually we wrap them up using waterproof paper to protect, of course, from the rain. So if you want some simple rules to avoid problems with timber, use always dry timber. And remember to check the moisture content of wood on the building site when you will be a check engineer using this moisture meter that I showed you before. Protect timber from direct contact with water, rain, so avoid as much as possible that the timber gets in contact with rain. And last but not least, allow timber to move due to the environmental variation. So timber must be able to move without being constrained, like the example I showed you before. Okay, so this will be everything in terms of woods and moisture content. Any question something that we want to clarify before we move to the next topic. Okay, so next topic is that dependency of the strength of wood also on the load duration. We already mentioned this, if you remember yesterday, actually the day before yesterday. This is a different behavior compared to steel, of course, to concrete. You can see here, quite interestingly, we test wood under short-term ramp loading. What does it mean? It means that we have a piece of wood like this. We put in the laboratory into a strain apparatus, for example, into a press, and we apply a load until this piece of wood is going to break. This load that we apply is monotonically increased, so we start from 0, then 1, 2, 3, 4, 5, until we get the value. And usually this load application is in about 5 to 7 minutes. So from when we start the test until the end, usually we have 5 to 7 minutes. Okay? And we measure a certain value of strength. This is what we call compressive strength, or tensile strength, and so on. Now, suppose that this ramp loading test, instead of being carried out over 7 minutes, was carried out in a fraction of second actually, like this. So very fast. Would we get exactly the same strength as before? The answer is no. We will get higher strength. We will get, you see, up to 50% more strength. Now, suppose to go the other way around. Rather than applying this load in 7.5 minutes, we apply the same load in 1 year. So we increase with this load very slowly, in order to get the value after 1 year, or after half a year, so get 6 months. Would we get the same strength? No, we will get less strength in the same specimen we're talking about. We get, you see, 30% less. So this is an evidence that the wood material, the strength depends on the loading rate. As I was mentioning on Monday, this property is typical of wood and of another material, of glass. Also, the glass has the same kind of behavior. If you load it fastly, you get stronger value than if you load it very slowly. You see again this plot here, 5 minutes, the ratio between the strength and the strength over 5 minutes obviously is 1. 1 second, 10% more. In 50 years of load application, 40% less. Now, the question for you, why are we interested in strength values for different load duration? When you design a timber structure, why do you think it's important to know the strength for different load duration?
Because of the anisotropy of the wood.
No, the anisotropy was already taken into account. Not necessarily by the load duration. I mean, the anisotropy we already know this way is better, this is worse, and so on.
But for the anisotropy, the kind of load is important. So
No, we were talking about why is it not. This ratio will be the same in all the directions.
but if the load is up mid or in 1 point or in 2 points.
No. If the load is loaded is applied 1 point or 2 points, then the strength will be different, but not over time, at the same instant. This is another phenomenon.
The collapse path.
The
collapse path.
What do you mean for collapse path?
With a piece of nice structure.
Yes.
Collapse.
Yeah.
The other pieces will instantly higher
Value. Yes. No, the reality is not this the reason. The reason is that any other idea? In which sense for the building? Let me be a bit more specific. For example, we have a residential building and then we have a storage building. So what would be the difference in this case? Yes? Well, in one case we would have a load always there for 50 years. The other case, Residential building, people may come and go away. What's the difference? Okay. For the storage building, which value of strength would you use? The strength for 5 minutes, for 1 second, for 50 years, for 1 year? For a storage. Deposito di carbone. Libreria, or library. The library will have all these books there for 50 years and more. The long one. Because in this case, the load is a long duration load. Okay? For an earthquake, which load would you use? Which load strength would you use for an earthquake? 1 second. 1 second is a bit less, but yes, more or less. For sure, more is closer 1 second. Could be 1 second, 1 minute would be, okay? Just 30 seconds, 1 minute. Okay? So we are interested in this dependency because the load duration is different depending on the type of load. So we will have to take into account this when we are going to design our structure. How are we going to take into account? Using, in the general formula, you remember how to calculate, I'm asking now about concrete, since this is the only structural exam that I'm sure you have already passed. So, characteristic compressive strength of concrete is equal to you must, all of you have already passed reinforced concrete, so no excuses if you don't know this. So characteristic strength of concrete. How can I calculate characteristic strength from? Actually, sorry, I made a mistake. The design strength of concrete was the question, not the characteristic. Now you can answer. The design strength of concrete equal characteristic strength of concrete divided by safety factor gamma n, gamma safety was called, gamma n, I don't remember now. Alpha CC, okay. So partial safety factor, characteristic value, what is alpha CC?
The type of structural system.
No, not really structural.
Different for beam, slab.
Yes, it would be different only for very slender slab, would be 0.80, if I remember well. Otherwise, always 0.85, if you remember. Okay. What does this coefficient account for? Why is never 1 is always less? 0.85 or 0.80? It's, well, it's related again to the creep behavior of concrete, if you remember. I told you that for long-term duration load, the strength would be a little bit less than for a short duration load. So you see, this 0.85 is similar to what we are talking about now. It takes into account that for long duration load, the strength is a little bit smaller than for, let's say, short duration load. So for reinforced concrete, it's called alpha CC, equals 0.85, 0.80. For timber, it's called modification factor, K mod. So for timber, we will have a similar formula, except that for timber, for example, FMD, design strength in bending of timber, will be K mod times FMK divided by gamma n. So the K mod is called modification factor and accounts for the influence of load duration, strength, and also influence of moisture content on strength. You remember before we said that the strength is affected by the moisture content. Remember, we said that the higher the moisture content, the lower the strength. So, how can we take into account the effect of moisture content on strength? It's all accounted for with this same coefficient K mod. So, K mod basically takes into account two aspects, two phenomena. One phenomena is the dependency on the strength on the law duration, and the second phenomenon is the dependency of the strength on the motion content. If you want, K mod is the ratio between the strength property assessed in standard condition. Standard condition means, no, sorry, say it again. The modification factor K is the ratio between the strength property in non-standard conditions and the strength property measured in standard condition, which means at the motion content of 12% and for a test duration of more or less 5 minutes. Okay? Clear? So we will replace alpha CC with K mod. Keep in mind that K mod depends on it's not a fixed value like for concrete 0.85. K mod depends on load duration. We go down up to 0.5, up to 1.1, and also depends on motion content. Clear? Okay. Creep behavior. Creep is another important phenomenon that we have to take into account when it comes to designing a timber structure. First of all, what is creep? Creep is a phenomenon that can be investigated by performing what is called a creep test. What is a creep test? You have a small block of material, wood, of concrete, whatever beam. Then you apply a load, Q prime or sigma prime on this block, on this beam. So this load, what is going to cause on the specimen? It's going to cause a deflection of the beam and a deformation of the cube. Now, if we were on testing a steel piece, how would it be the diagram of, let's say, this is a steel beam. I apply a load E, and I keep the load constant over time. This is the deflection, eta, time, deflection, load T, time T0, I apply the load. What do I get here? When I apply load P, I will have a certain deflection, elastic deflection, right? Now, if I keep the load constant over time, forever, for example, what kind of diagram I will get for a steel structure that? So how would this eta T diagram look like? Are you sure? This one is not a stress deformation relationship. This is deflection versus time. So the load is kept constant over time. How can I expect the deflection to change over time for a steel beam? Constant. Why is constant? Because the steel
is plastic.
It's elastoplastic.
Plastic material,
Not a viscous material. So for the steel would be something like this. Now, if this beam was made of concrete, how would this curve look like? The one that you were saying before, exactly. So this would be for concrete. So there would be basically what we call a creep deformation over time. This creep deformation over time, as you can see, there is a curve like this. So the creep phenomenon is this phenomenon characterized by an increase in deflection deformation on the same load over time. The rate of deformation, as you can see, is higher at the beginning. So if I go to estimate the derivative of the deflection over time, this is higher at the beginning, and then it tends to zero. So if you want, the rate of deflection is higher at the very beginning, during the first minute, and then it goes lower, lower, lower. At the end, it becomes almost a flat curve. Okay? This is called creep phenomenon. For concrete, you remember how did you calculate, how did you take into account in reinforced concrete design the creep when calculating the deflection? Okay, so T infinite is 0. Okay, so let's say that we are interested in calculating the deflection, the total deflection. So the total deflection for us is the maximum deflection that we'll achieve at the end of the service time. At the end of the service time is indicated sometimes with T infinite, which means 50 years. So A total deflection. How is it calculated? Okay, eta elastic
Times 1 plus
times 1 plus
T
5 T infinite is 0. Okay? So basically, we said that the total deflection is the sum of the elastic deflection plus the viscous deflection. But the viscous deflection, if we assume that our material is a viscoelastic material, then we can say that the eta creep can be calculated by multiplying the eta elastic times phi of T0, T infinite T0, where phi is called creep coefficient. So if we have a viscoelastic material, we can use this formulation here, which of course then leads to the formulation that your colleague said before. So the total deflection can simply, or the viscous deflection at the end of the service can simply be assessed by calculating the elastic deflection and multiplying it by 1 plus the creep coefficient. The creep coefficient is provided by the regulation. So there are some formulas to calculate phi of T infinite T0. Okay? Now, what does it mean what does the assumption of viscoelastic mean? It means that, like for elastic, for example, if you say I got an elastic material, it means that if I got under a certain load a certain deflection eta, if I double up the load, also the deflection will be doubled up. This means elastic. Okay, viscoelastic material is exactly the same concept. If for a certain load I have a total deformation eta, then if I'm going to double the total deformation, is a final deformation here, if I double up the load, also the final deformation will be doubled. So this means, for example, you see here, I start applying a small level of load on my beam, on my specimen, and I've got a certain value of deflection. Then I double up the load, the deflection will double up. I can continue this up to which limit? Can I continue to double up until which value? At a certain point, this property will not be true anymore. So there will be a limit. There will be a limit above which what is going to happen is that if I apply a slightly higher load to this limit and I keep the load constant, what is going to happen is that, you see, I will have a creep behavior, but then at the end I will have a failure. So while before, by doubling up the load, I was doubling up the deflection, but I didn't have any failure to the beam. If I pass this limit, I will end up with a failure to the beam. Why? Because the level of load is too high. In this case, you see that the failure will occur towards the end of the service line. If I keep increasing the load, then what is going to happen? The failure will occur before. The higher the load, the sooner the failure. at the end, limit case, I apply a load equal to the strength of the wood, then I got immediately the failure. Okay? So all these points, you see, all these black curves concern specimens that have been loaded below this limit. So they just creep over time, they just deform over time, but they don't fail. Above this limit, which is now denoted with this red dashed curve, above this limit, I've got specimens that at the beginning they creep, they resist over time, but eventually they fail. Of course, the higher the load, the sooner the failure. You see, all these curves all these points are collapse points. So this red line is called limit of creep rupture. What is the value of what is this value of the creep rupture? If you remember before, when we were talking about K bond, we said that for a low duration load, so for a load that is going to remain on the structure for 50 years, then the K mod should be 0.6. So basically, this limit is K mod times F. So it's about 0.5 times the strength in the short term. So basically, for a level of load of stress less than 50% of the short term strength, we can say a viscoelastic behavior, even though I would say viscoelastic in this case is a simplification because we would have a kind of non-linear creep, but just forget about it to make it simple. Viscoelastic behavior below 50% of the strength, of the short-term strength, and instead creep rupture, so deformation with final failure, above 50% of the strength. Okay, it's clear? If you want, here you can see the connection that we have between the creep phenomenon that we use to calculate the deflection of the beam and the dependency of the strength on the load duration. So the K mod factor that we saw before. Yeah, sure.
Until the K mod line.
Yes.
Correspond at 50% of the strength. Okay. I have a viscoelastic period.
This is an approximation. Strictly speaking, let's assume it this way. It's not in this way, it's not linear creep, but for simplicity, let's say it's a viscoelastic behavior. Yeah.
Then, separated this line.
Yes.
I will have only creep.
No, above this line you will have creep at the very beginning. Look here, this curve here. Creep, this is called primary creep. You see that there is some increase in deflection. Then you have a secondary creep, this curve is almost linear here. And then we have what is called tertiary creep. So the rate of deformation increases again until you get to deflection. Okay? Other questions? Now, how do we do this creep test? This is an example of the creep test that I carried out 10 years ago in New Zealand. So, a piece of timber, two blocks in between, so two basically blocks of reinforced concrete hanging on the beam. And then here a potentiometer to measure the increase in deflection over time. So, 5 is the symbol to denote the creep coefficient in concrete structure. Okay, for timber we don't use the symbol 5, we use another quantity. So only the notation different is called Kdef. So Kdef is basically the creep coefficient of timber. The creep coefficient of timber does not depend on both T and T0, it just depends on the difference between T and T0. So it's a function of T. Final T infinity, if you want 50 years, minus T0. So the creep coefficient is tabled in the regulation. The Eurocode is in the technical regulation for construction. You find the table like this, saying that for solid timber and for a certain setting class, you have a certain value of the creep coefficient of timber, Kdef, in the long term. So for the calculation of the final deflection. What does it mean serving class 1, 2, and 3? This is something that we will study later on. For the time being, I just tell you that service classes depends on the timber moisture content. So, serving class 1, moisture content of timber less than 12%, serving class 2 between 12 and 20, serving class 3 between above 20%. As I anticipated before, the higher the moisture content, the higher the drip coefficient. So just to give you an idea, if you have a serving class 1, so if you have a timber beam that has been put into an environment, heated environment where you have a lower moisture content, the drip coefficient is 0.6. What does it mean? It means that if you measure in the short term 1 centimeter deflection, this 1 centimeter deflection in the long term, so at the end of 50 years, will become how much? So if you have 1 centimeter in the short term, so you apply the law, you measure now 1 centimeter, you come back after 50 years. What will be the total deflection after 50 years? If you are in service class 1?
1.6.
1.6. Exactly. If you are in service class 2, more or less the same, 1.8, you can change it. Huge change if you are in service class 3. So the 1 centimeter becomes 3 centimeters. Okay? This is another reason why it's better to avoid to have higher value of the moisture content. Of course, creep shall be considered when evaluating the deflection. So for serviceability mistake. The elastic deflection must be multiplied by the coefficient K. So as we said before, elastic deflection times K def will give you the creep plus elastic deflection will give you the total. So for example, basically for timber, we will use the same formula except that we will replace I with K def. Okay? Otherwise the formula is the same. Okay? Now just to try to conclude, strictly speaking, as I was saying before, creep is a very complex phenomenon because strictly speaking, you have what is called mechanosorptive creep. What is mechanosorptive creep? Basically, it's an increase in creep due to moisture content variation. So the creep is usually performed, the creep test is performed when you have constant environmental humidity, so constant moisture content. If you start changing the moisture content, then also the deflection increases. You can see here, if you do a creep test in constant environment, then you get this kind of curve. If you start changing the relative humidity by making some cycles, for example, you have cycles of relative humidity between day and night, between seasons. So if you do some cycles of relative humidity, you can see that the curve is going to increase. You have much more deflection in the long term. Yes.
In Italian,
fenomeno meccanico assorbitivo. È una italianizzazione dell'inglese. So, the changes in moisture content makes an increase in deflection. So the difference between the total curve and the curve in constant environmental conditions is called mechanosorptive deflection. Now, just to show you some tests that I carried out more than 10 years ago, this time in Trieste, in the University of Trieste. This is a connection, you can see here, this connection between a concrete slab and a timber beam. It was basically fixed in this way of the specimen. And what we were interested at the time was to study the creep behavior of this type of connection. So when you connect timber with concrete, you can expect that this connection is going to creep over time. We were interested in this phenomenon of mechanosorption. So what we did, we applied a load constant over time with this lever apparatus. So basically you can see all the specimens were loaded in order to increase, to apply a constant load over time. This was inside the climate chamber. Climate chamber is a place where you can basically control the environmental conditions. You can control the relative humidity, you can control the temperature. So we kept the temperature constant at 20 degrees, and we changed the relative humidity. The results, so this would be what we called before creep coefficient. So this would be the phi. So for this connection, you can see that as far as the relative humidity was constant, we found the normal creep behavior, and then when we started doing the cycle of moisture content, you can see that we have an increase in creep coefficient. So this difference, of course, you can see a quite significant scatter of curves here, but if you do the difference between the average, this difference is called Meccano-sorptive creep. Now, we don't want to go too much into detail, but just to tell you that, strictly speaking, to study the behavior of creep materials, of material with Meccano-sorptive creep, is quite complex. Because, you see, for a linear elastic material, there is this simple relationship epsilon equal to sigma divided by E. If you have a viscoelastic material, this algebraic equation becomes an integral differential equation. If you have a Meccano-sorptive creep, even more complex. Of course, this is just to show you that from a rigorous point of view, this problem of a material like wood is very complex to solve. Of course, we are not interested in numericals, but we are not interested in this kind of complex equation. We are interested in being able to design an infrastructure. So some simplification of math. What kind of simplification of math? Okay, let's say if we want to solve the structural problem, we should use numerical method, finding energy models, but as a designer, if you want to design an infrastructure, the most important, the most useful thing is use approximate analytical method. In this case, we use what is called effective modulus method. What is the effective modulus method? The idea is that if you have a viscoelastic or even hyperviscoelastic material like wood, this can be regarded as if it was an elastic material by simply changing the value of the module of elasticity. So, when we calculate, for example, the deflection, we use always the same formula, 5 divided by 385 times Q times F to the power of 4 divided by E times I, but instead of using the normal Young modulus, we use the effective modulus. The effective modulus, you see, is the Young modulus divided by 1 plus 5. In the case of timber, we E divided by 1 plus KF. So, you see, if you need to calculate the deflection in the long term of the timber structure, you simply calculate the times deflection and you multiply by 1 plus 5, or, as I said before, if you're using software like SAP 2000, instead of giving to the software as an input the Young modulus E, you give to the software this fictitious effective modulus E prime, E divided by 1 plus KW. So you reduce the module of elasticity of the material in order to increase the deflection, takes into account of 3 Meccano-sorption. So, for timber, basically use the KF as a 5 after 50 years. Okay, so thank you for your attention. We are on time. Now, tomorrow I think we haven't done this stuff. Okay, thank you.